before starting with the second part, I want just to ask you about the deterministic augmentation, which seems to be possible in case you have somehow a good mathematical model of your physics, the physics of the representation you are going to describe. But I believe this is not always possible, because a good mathematical model, it is not always available. So in that case, how much do you think is critical the knowledge or the availability of a mathematical model to implement your technique based on deterministic data augmentation?
Okay, if I understand well, the concept of this is that how, for example, this model can fit it for different scenario or different application. Am I right? Okay.
Yes, in general. Yes, in general.
In general, as I state that exactly, a parameter sigma p is very important one. The noise variance of the features is exactly those parameters started and helped us to fit our model to any different scenario. And finding and tuning that one was very important. And for this reason, also, we expanded one very important part of our study exactly to find the optimum value for it. Because exactly through the graph that I presented that, okay, just gives me to show here, exactly through this graph that I presented, saying that, look at this graph, is very brings interesting matter to us, because for instance, if we say that the sigma p is 0, meaning that no augmenting data, and if we started, for example, increase it, and in our scenario, I mean that for our scenario with the exactly our target, the bunch of the UAV that we use, the sigma p, if goes from, for example, 0.3, leads to model again as an overlap the features between the class A and the B, and it started again to cause the overfitting for the network. This sigma p, that's maybe a more and detailed concept of its mass and why is important and which effect it brings for fitting is the next step. But I can say an answer to this question through using and finding the optimum value for sigma p, we can fit our model to different scenario.
Okay, thank you. So I believe that it's now the time to move to the second one. Please, Marco, are you ready?
Yeah,
of course. You have to remove. Okay, the slides are the same. Okay.
Yeah, and really thanks to my colleague, because she was so clear in depicting the wall, and also thanks to your to the last question. I think that Ned answered very well to the last question, and I wanna highlight another time this point. The matter is that exactly by finding this specific way, we can compensate for to the lack of precision about the model. Because actually we are getting something like an expansion of the feature space in a syntactical way, of course, but we are exactly inserting, we are exactly merging this lack of precision inside the variables that are already defined in the model. So just like, and I will show you the process better. Anyway, yeah, the answer is that one, that using the sigma p, we can also trim to compensate the model effectiveness for this. Okay, I think if Neda, you can, okay, thank you. Okay, so, condividi. Okay, do you see my screen?
Yes.
Hello, do you have?
Please go ahead.
Okay.
Yeah, please go ahead.
Okay, I don't know if you see my mouse pointer or not.
Yes, I can see that.
Okay, thank you. So again, very glad to be here. Good to see all of you, etc., etc. And let's go straight to the point. Exactly, I will like go in deep in the more mathematical aspects of the wall solution that Neda just proposed here. Because the point, exactly as Neda told, the point is to show that another methodology is possible, okay? So imagine all of this like by a conceptual standpoint, of course, proved with experiments also, but the main point of my part will be to show you actually what's behind the definition of this and what's behind the actual achieving of the results. Because we will play like exploiting, exploiting maybe is the right word, with exploiting the mathematical nature behind the deep neural network concepts. So what again, probably I will repeat something from I will say some similar things to Neda's talk, but we decided to repeat some of these concepts because they're quite important in our opinion. So at first, let's talk a bit about the paradox of training for a deep neural network. Okay, we have a nice robot here. The robot must recognize some class of something. So we have maybe a word there. We have the apple word. And at the beginning, the robot actually thinks that everything is an apple. Everything. For the robot, it's exactly the same. It's like a plain whiteboard mind about something. It's just a little child thinking of it. We have another extreme for this because if we do something to the robot, like if we take it to very, very, very bad schools, actually, we could have the exactly opposite for this. Actually, we had a robot that is totally agnostic about everything here, and he will not be able to recognize nothing as the object that we are asking him. And here, these two sides can be conceptually mapped on concept of undertraining and overtraining. I mean, like when I am undertrained, I see the beautifulness in everything that I see. Well, because I don't have a way of comparing with some concept that I have in my mind. While if I am overtrained conceptually, I will philosophically, I will look for the perfection. Looking for the perfection, actually, perfection cuts away the real world. So the network will begin to be too much really with very, very hard flavors to accept the kind of data that it has to accomplish with. In the middle, between these two things, there are some like middle cases where actually I dig in to classify something. Maybe at the beginning I classify similar shapes, but maybe not other ones without a specific reason. In between of this, and if you look, it's quite interesting that actually this is quite a linear path from this point to this other point. So we have somewhere in the middle where actually I achieve my optimal accuracy, precision, and my optimal functionality. Look, that this kind of sorting on this domain from here to here is something quite interesting, not just because of the concept, but also it's something that, of course, could be mapped on some kind of domain. So if we map this behavior on some kind of domain, we can get back the concept of getting the right something, for getting the right training, just putting our robot in some kind of precise and right situation for learning the best. If you think about this is a bit like it's a good way to deal with this kind of problem. So because actually, at least conceptually, we are reducing the degrees of freedom. We are reducing the cardinality of what we are thinking about, just reducing it to looking for one variable. So let's dig about this. We can map this variable on something. So as you can maybe imagine, we are quite agnostic. Agnostic towards the deep neural networking concepts because, okay, that's quite a really nice instrument. But anyway, it's something that in the last years got really like a black box dominated by computer scientists, which actually all focus so much in the single mathematical aspect on them, or they focus on the wall, actually just looking at all of this just as a black box without any concept of what it's inside. While deep learning is not magic. Deep learning actually is something that is way simpler than this. So let's come back a bit to the robots. We have the Apple. We are classifying things respect the Apple word. Already, this is in magic. I mean, from the Apple word to the Apple object. Oh, wait, how is possible to map word to image? Okay, but we can imagine this as a simple, like a database, like something in the middle, a translational layer between the actual word and some kind of more detailed source of information. It can be an image, a sound, the touch, the feeling, the smell, everything. Anyway, we have more than just 5 bytes for characterizing the object that we are trying to classify. And imagine that we are actually dealing on the view. Actually, the robot is looking at the apple and it has to understand if the apple actually is an apple. Okay? So when we have this apple, if we think at this really starting from the basics, the point is that actually there is some kind of simple machine learning, because this is machine learning, this is not deep neural networking. A simple machine learning something, a network, okay, which actually takes an input expressed just as a vector, and towards the output, it gives a final outcome. Yes, no, apple, or that's not an apple. But if we write all of this in this way, okay, when we get to the final point, actually, and the final point, we could say that, okay, there is a binary decision, but finally we can map the outcome for this classification on a linear domain that is continuous. And we can just put some threshold function for detailing what's apple and what's not. And imagine that, as usual, maybe we put sigmoid, we put the last layer activation layers, the last layer activation function, and this takes as an input a real variable. So it means that here, despite I just speak about class 0, class 1, class apple, class not apple, actually this is a real number. It's a real number that's mapped over a function domain. So we have the x variable, and the x variable in this case is the appleness. How much an apple is an apple? Finally, it seems quite like between the stupid and the childish and the magical, but the final concept is this one. What's the appleness here? Actually, we are digging to the appleness because we are looking to find a variable that is ness something to understand if we can map our problem on this kind of formalism. When we talk about the x, and we come back to the structure of the normal machine learning network, we can say that at the beginning we have, of course, a flattening. So flattening, it means that every kind of information that we have is just a vector of real numbers, as an example. And if we go if we think a bit about this, we can say that this whole function can be defined more than between a last point, a last step that is like defined on a real variable, why I should consider this an intermediate step respect a real variable. Why I can say that this is exactly just a function of a vector. That's a function of my input vector. So actually, if you consider this, we are simplifying our our system model for this, because we have something that just it's transforming a vector to a real value again. So we have this intermediate layer when it's where a domain flattening is happening, because I am getting inside with a lot of numbers and I am getting something that is just real. Okay, because here after I have the real codomain in input to the last layer. So let's dig a bit and let's try to understand all about what is this, because if we, I think sometimes we lose the point about this, because we can write all of this in the classical neural basic writing. I put all my neurons together, I exactly write my equations, I put all the stuff, and I have some kind of complicated, more or less equation if I have more layers. And in this equation, actually, I am exactly putting a transfer function between my vector and the output. But if we just dig a bit in the math of this, we can develop this just as in a simplified way that actually can be simplified more, just remapping the coefficients. If you look at this, actually, that's not something, it's something so trivial. But if we jump from this one to this one, actually, we are putting inside a concept. Because if I write everything as this, I can say that this is nothing more than a vector projection. So what's happening here? Like what we are saying, that the wall of the deep neural network is just a projection operator. If we think at this, the problem is getting something way more deterministic than the typical concept of deep neural network training, because training is based more or less on some kind of randomness, while here it seems that there is just one deterministic way to model all of this. So what's exactly the vector here, and what's the d vector here? What's all of this? Let's come back to the domain of our signal, the S vector. We have in our case 4x4 images, images made by 4x4 grid of pixels. So we can define a vectorial space. And in this vectorial space, I have a lot of different images there. I have these images. And finally, I have my apple. Now, if you think of this, how my apple is an apple? The apple is an apple because I guess that my apple vector will have some kind of parallelism, respect a stored vector behind, because actually they are keeping the same information. Not same, similar information. But what is similar? Similar information is a grammar. It means that in a vector, we have specific rules that are joining together the terms of the vector itself. So if I consider this as a projection, I could say that the appleness is just the projection on a base vector representing my target class. Okay? When actually I am dealing in this way, I could say that, wait, of course I know the S, but I am defining my network. So as I am defining my network, I need some V term that actually is unknown. And here is the training. Because in the training, and of course, wait, the concept is that apples, if I take different apples, the apples should be parallel to apples, because actually there are common features. Features considered as rules in vector structure. So we are totally mapping conceptual high-level concepts to pure mathematical simple concepts here. As this, when I consider the final layer, as I need to determine my best base vector for determining my classification, actually, I have in my last function, I have this degree of freedom, or actually I have this coefficient, and this coefficient is something that is again tunnable. So I can actually move this like the zero value to actually trim exactly the threshold value for dividing between what is apple and what is not apple. So actually defining my appleness. So why I am going towards all of this? Because as this, actually, we can say that we can reduce all our information that we require just to not just vectors, but to grammars. And grammars, as they are deterministic, they can be defined parametrically. That's the point. Here, if we come back on if we come back a bit, we can say that, of course, what's the training? The training is that I have here 16 variables, 16 unknowns. So I want to find the best B vector for which actually the whole function, the decisor, the G, the last layer function, the activation function of the output of this must be higher than a threshold. I am getting rid of B0 because I don't want to complicate this so much. And when I have the boundary conditions, so when I have a beautiful set of apples, yellow, white, red, no, white maybe not. Anyway, all colors and smells. And this is my training set. Again, I can define this following some kind of rule that I have in mind. We guess that apples are almost parallel to apples. If we define each apple as a different vector, we can go back to this definition where actually I can find one ideal V vector that is able to represent all the apples that I have, because I'm getting the features that are in common for this. So I can say that if I want to get the best V, the best apple V, the best apple vector, I should do something like an averaging of these vectors over some kind of operators. What's this again? This is mathematically quite straight. Practically is the backpropagation, okay? So in the backpropagation, if you look here, the backpropagation, it's exactly the feedback tuning of all the unknowns on the back, because I presented you a closed form equation, but of course it's not as this, because I have several conditions to fit. So I'm doing backwards the propagation on the weights, finally to get my best V vector. But again, the final is that my V is just a vector, okay? So it's so simple, the point, of course not, because actually I have at least at the beginning, I have not so many, in a machine learning approach, I have not so many variables. So I am exposed to an overdetermined risk. I mean, I have more boundary conditions than the number of variables that I deal with. And actually, in the case of overdetermined system, we are in the overtraining case. And we are not able, the robot is not able to understand nothing about the apple. He doesn't know neither how is made an apple. And why this? Because if we come back to the backpropagation, actually, when we do for a lot of samples, the backpropagation, the average of the weight tuning gives 0. And gives 0 because it's the randomness of the world. Why? How I can get rid of this? I can get rid of this increasing my number of coefficients. But how I can increase the number of coefficients? Increasing the neurons. Here is my overfitting, and this is something that is really bad. And here is where the deep network engineers must pay attention when they design the network, as Ned, as Dr. Rojani showed before. Her network was exactly trimmed considering several steps. And also, maybe in this way, the feature checking is a bit dumb, because of course, if I just put the vector, there are several transforms that I can apply, and actually the vector is not anymore, the apple is not anymore an apple. But for this, we have the solution, and it's just a implementative solution. It's not magic. There is nothing magic more than this. We go from the machine learning to the deep learning. The deep learning, I increase the number of layers. I increase the cardinality of my system. My V vector is not anymore by 16. It's maybe 256, it's 1024. And I'm increasing cardinality of my space. And I'm introducing some step behind where actually I find a way to code my information in a way that actually I can save what is important on a domain that actually doesn't change. In an example of the radar, in the radar, like the FMCW, like the one showed before, this coding can be, as an example, the FFT, because FFT provides some kind of resistance over some effects that can happen on a scene, like rotation. If you do the image FFT of a rotated images, actually you are getting the same absolute value for the 2D FFT. So we are coding the information, keeping what is important for us. And the coded data becomes the new classifier input. So here we have this plot where actually we had the machine learning that gets an overtraining before and an overfitting before, just because it's simpler. And I am just complicating the stuff just to increase cardinality to avoid the overfitting that is got when we get the excess of back propagation with respect to the structure. Why I'm telling you all of this? Because if we know about all of this, we can think about how we deal with this. If I just want to provide vectors that have some kind of rule inside, why I can't provide a base generator function, or rather a deterministic parameterized function that can give me something that is similar to the final measurement? If we consider as an example the case of the apple, the most important thing is that this base generator function will be defined with respect to a base of arguments that actually is not anymore the number of points in the traces, but it's a higher layer level of abstraction where actually my arguments are easily coded in a very, very, very short kind of vector, because we can put on them complex concepts, because we are augmenting respect characteristics that are meaningful to us. And this is another important point, because honestly, and this is like almost this is almost a like political war, because the really world of DN engineers is really split. There are the people that think that, oh, look, the deep neural network will always find the best way to manage the features and find something. But of course, we have also sciences like the explainable artificial intelligence, and we have the overtraining issues, because actually we finally don't know what are the features that are considered meaningful inside. And that's not good. Actually, it's like having a beautiful horse doing a pat on his back and looking at him running away while we don't know where actually he's running. Okay. Here, in this case, if we define the arguments as this, also this is human readable, and it can be compressed. I mean, I can represent the same trace of 100,000 samples with maybe just 10 numbers, 15 numbers, 20 numbers that are actually the arguments for the function. So if I put in my training algorithm not the input from some file dataset, but I put a piece of code managing this, actually I improved the equivalent capacity, the equivalent memory capacity of my system of thousands of times. So I can make more samples, and I can have data sets that are ideally infinite. When we back, as an example, in case of the drones, and we come back to the drone stuff here, when we deal with drones, actually, we have a lot of information we can think about. We have the power of motors, we have the physical parameters, we have blah, blah, blah. We have a lot of properties. And they are exactly the properties that actually are put in the parametrical model made by EM solvers, because EM solvers are parameterized, and actually EM solvers are nothing more than this. EM solvers are exactly this. The matter is how the F is calculated. If the F can be provided in an analytical way that can be also not perfect, because of course there is the risk of not perfectiveness, but we can manage it, and after we will show you how. Actually, we can have the same kind of results in a totally with an astonishing gain on the whole process. For the way this, so we move. We shifted from datasets, training datasets from apples to drones. The argument string is changed. And finally, we have some, for each engine, we have a vector, and the vector is based on mechanical properties that are quite measurable, and are quite measurable. And maybe you are saying, oh, wait, if I can measure, why I need the augmentation? I just can measure all, and I get measurement data to make vectors to actually fit my training. But the concept is that as the structure of a drone is known, if I have a quadricopter, and if I have a quadricopter that is actually capable of flying, this quadricopter can't have 4 helix, all one on top of the other. Otherwise, it doesn't work. Otherwise, it's a helicopter. So finally, I can determine a subdomain for my parameter space. And on this parameter space, I can introduce the variability of all the copters that are existing, but following the grammar. Here, following this, as an example here, let's talk about this generation function, the meaning of this, because generation function we compare with the physical process, because we need to classify respect to real measurement. In the physical process, we have an actual scenario, we have a transfer function, and we have the final output. The generator function is just a deterministic form for what happens between the human, the compactable, the compressible set of information determining one specimen or another specimen, and a series of transports that actually leads to the simulated measurement. And finally, if I write this as a chain function, I can say that as I have like the apple inside the physical process, I have my idea of the apple inside as the input of the generator function. So here maybe I have 16 bytes, and here I have maybe 3 bytes, just an example, color, category, and so on. And finally, I will have an intermediate block, which actually produces a vector that can represent the center point for all the variability of objects that are red apples. Just to make a fair example, a simple example, I have a quadricopter. Quadricopter has a side measure, it can be determined by the measurement of its sides. Okay, its sides. Okay, so I have one small quadricopter of 10 centimeters, one of 30, one of 50 centimeters, but they are still quadricopters. So if I determine this in an equational way, then that's exactly the digital twin, because digital twin is this one. The point is that in the digital twin, the parameters are inserted as numbers and are used to actually tune some 3D model, some parameters of a three-dimensional model. So I have the target. One important thing that also is an open point in actual literature is that I need this data to be coherent. To be coherent, I must consider that the actual sensing blocks considered are the same, and this can be considered trivial, and there could be someone that disagree with this. But if you disagree with this, actually, you are not getting to a deep neural network that is not working, but you are getting to a deep neural network that is mixing between what's the apple and how you see the apple. In our case, I must, as an example, in case of the robot, I'm using the vision for both the case. I can't put like the touch on the physical, I can't put the vision on the generator function while I'm using the touch on the physical process. And this is quite, this seems quite trivial in our cases at FMCW radar. This is quite trivial, but actually, it's actually the point is that if we consider this geometrically, as the sensing process modifies the shape of the measurement vector, and I put all the stuff inside my system because they are just numbers, on a bunch or in my vectorial space representing not just the object, but object plus process, I will put all the other numbers rest in different scenarios. The hearing of an elephant, of a car, the smell of an apple. And the matter is that, given the cardinality of the system, I could have that the smelling of an apple is equal to the touch of a cat. I don't have a way, there doesn't exist a way to be absolutely sure that these are not overlappable, because it's just signal. Being just signal, they can be as they can be. So a car, hearing a car can be an apple, and smelling an apple can be a cat. So finally, here we have the problem of making the right generator function, considering the dispersion of respect the parameters. Because I agree that we agree that there can be some lack of precision in the model, but there is difference from totally misunderstanding the process that we are dealing on and not putting some additional detail. Because grammar is this, is understanding the rules behind. As an example, image to sound. This is a cat. I don't know if you can hear the sound. Anyway, it's a soundgram of something that finally is a cat. This is the image of a cat coded as a sound. Or a very, very simple example, sound to image. So if I put this, I can put this compared with other vectors where actually I have the fetus photograph. I can, but I must know this when I define my training set. I can accept to put together tomography and fetus and echography and fetus, but I must consider it in my generator function. And this can seem something like to be worried about, but also it's a seed of it's the starting point for something way more powerful. Again, let's talk about our specific scenario. In our specific scenario, we have the chain of blocks, we have the wall system, and we have the transfer function. And this is nothing more than our scenario, actually. We have a FMCW, we consider in some way the target, we put the receiving, we put the operation there, and we get the dataset, okay? We are just replying this. So just to basics of radar, I transmit the signal with the FMCW, I consider the received echo signal, I'm doing the decorrelation and blah, 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 going through. If you see here, that's a very, very, very trivial based model. The matter is that the correlation characteristics as given by the exact process, despite the system is simple, they are strong. Because a cosine, in a world where every signal is a signal, a cosine is totally uncorrelated to the noise. F1 is uncorrelated to F2. So this is something that we can exploit, exactly getting orthogonal vectors. And considering this, we put the vibration in our case, so we get some kind of FM modulation, we have the static target, we consider the vibrating target, just to show you the triviality of this model, actually. I consider the vibration. Also, vibration was the point. I want to keep my system. I want to keep my model simple. I want to do it. I want to stress this point. I want it to be simple. So I reduce complexity. I consider just observation planes. I just say that, oh, look, I can maybe project the vibration on each engine towards a barycenter. Okay, I can generalize at the beginning. I can generalize because I never said that I want to know what are these variables since the beginning, because I don't need. I just need to determine a grammar between them. So if I am able to fit these variables on one case, just one case, or 10 cases, okay, 10 cases. But what are these 10 cases? These 10 cases are just the required the required amount of data to go to the central limit theorem. I mean, it's something that is basic of measurement, but the concept is that I am doing just one measurement, doing my best steps for achieving it. I can, as this, put all together something inside the function, and finally define this function because of argument as this. But this is defined finally respect a matrix. And I define this respect a matrix. A matrix is defined as respect a base. So I am exactly making a base that model my target in several possible ways, because it's a grammar. If we continue with this, of course, this is easily augmentable, deterministically augmentable. Everything is so nice, so good, it works well, and we can get a lot of money selling this because it's already working. Yeah, no, honestly, yes. We just must pay attention to some details here. Because as an example, okay, let's try to dig a bit more in the model. We are considering the complex. We are still reducing the complexity. We are still reducing it because we want to do it. We really want. We want to reduce complexity. We want to get to some kernel point for this. So here we are still dealing with the effect of the several bidirectional effects, bidirectional components, and so on. The point is that we changed a bit the definition just to have a better matching with an actual mechanical model, but we proved that actually we just needed to change the way of writing this vector, but actually we didn't change the values. So actually it was already working just with the basic definition as before. The point is that maybe this is quite, I mean, we are so proud, but maybe we are like talking empty. We are like emboldening ourselves. But maybe yes, maybe not. Let's think. Actually, we are engineers, so there isn't yes and no. We are shades of success. Okay. So let's dig in these shades of success here. So if again, if I define this matrix respect some details, I know that there is a relation between these data sheets and the final base. It's unknown this. But again, what's the matter here? It doesn't matter here. It doesn't matter here because I can start from a single simple concept that similar structures share similar grammar, similar structure of vectors. So if I define the grammar of this, actually, I can exploit this. Because if I keep this, I can say, wait, I measure two specimens, one specimen for each class. I do my experiments in a totally different scenario. I have the noise, I have the non-idealities, I have everything, but I am not taking this data, putting them inside the training set. And I'm not doing a random augmentation because otherwise I take all wrong features with me. I am just using this to provide just at the beginning, because I know that people usually say, haha, you put genetic optimization here. Yeah, okay, but it's just an instrument. Okay, because the focus now is just that we didn't want to find a better form to do it. And the single genetic optimization is quite simple because we are not considering so big amount of data. So again, we are just considering the range shape respect the front. So we are dramatically simplifying the problem here. We just take the cut and we decide to do the genetical fit respect our grammar to this measurement. We found here some parameters for the monocopter, for the helicopter, for the quadricopter, set of parameters, and I get a whole bunch of numbers. Okay, again, good that we are interested in them. Yeah, yes and no, because I'm not interested in the absolute values. I'm interested in them as they can be the center points in some multidimensional space where actually I can make my variability enlarging this cloud area. Because if we go back to the classes represented by vectorial bases, actually, if we, just as an example, if we zoom in inside like two features, so we are determining feature, we are determining geometrical locus for features. Indeed, the basic of SVM, as an example, is just to determine the areas on some kind of plane, actually separating between the class A and class B for points. I have my center point here, that is what I got from the genetic optimization. And the point is that I need to have my samples, I need to have my samples orthogonal, are related between them. I need to preserve grammar, and I need to preserve the clustering. If I fulfill these three properties, I got my point. Here, the point is that the risk is that if I do an excess of augmentation, actually, I am enlarging so much the scattering of my points that actually I am overthrowing points from class A to the class B. And of course, this is some kind of limitation, this is some kind of parameter that I should deal about. But if you come back to the beginning, is the one-dimensional parameter that moves between undertraining and the overtraining. And the phenomena is quite similar to this. It's almost the same, because the generator arguments are features. Features are arguments. We are doing augmentation in feature space in a random way. But putting noise, as Neda told before, she was really very clear for this. We are putting noise on feature. And this is the main point of this work. It's just this, the point of this work. So let's consider first point, doing vector augmentation with linearly unrelated vectors. So we are adding syntactical phrases. We are putting just a Gaussian noise on top of my matrix. Okay, let's do it. So just I cycle, I produce the number of samples that I want just because I produce 32,000 of samples of noise. I do the perform, I produce the phrases, I do everything what I want. I get my beautiful data sets here. And okay, and here I could say, okay, I did it. But the grammar must be preserved. The grammar must be preserved. It means that if you consider actually the relation between parameters, this relation is not casual. It's not random. There are orders of magnitude between terms. And if I am considering to expand myself on this space, I should consider that I can't put the same amount of noise for the radar cross-section, the amplitude, and the frequency. Because of course, I would actually introduce, if I just add the noise straightly, I simply would reshape the expansion, because I would compress some of the domain, a part of the domain, actually getting a biased augmentation. So for this, that's quite a simple step, because the point is that I want to trim I still want to have just one parameter. I just want to trim respect that parameter. So I change a bit the writing of this. We changed a bit the writing for this. And actually, we put the sigma p just as a percentage of variation respect the center point. If you consider as this, we can write that as the scale between features is this one, and we consider the radius of the augmentation cloud, the final the aspect ratio of domain when I put the augmentation, it's still the same. Because if I put the noise in this way, I am enlarging my points in a spherical way. So I am doing a right and logical uniform augmentation of my parameters. Last, and if we consider again that we must preserve the clustering, the classes clustering, we must consider that this sigma is limited somewhere. For this, Neda, Dr. Rojani had this minding of using machine learning here, and this was an amazing idea, because actually she found this intermediate step of using a simple instrument to actually do the trim in an automatic way. Because by the piece of code, the piece of implementation made by Neda in this case, actually we have got a closed loop system. So the system is able to train itself in a feedback way, because we know what's the optimal for sigma p. Is the optimal with the highest accuracy, maybe precision, if I had some data sets for checking. Otherwise, I just need to say that the clustering is doing well, and I can have metrics, mathematical deterministic metrics for doing so. So here we have the trimmer that is exactly this. And we finally find out space that also we found that for different scenarios, it's always in the same area. It's still some work that we are still doing. Probably we will, in the conclusion, I will just put the idea for this, but we are getting exactly the same behavior. So it means that here there is something meaningful. Also, if you consider that this domain goes between the 5 and the 25% of this. So it's sensical, also respects some Gaussian theories. Anyway, if we go on bottom, we don't have augmentation. If you go over, we have the class level mismatch. We just have to dig in the middle of this. And finally, the point is that starting from the reference specimens that are very different than the final, if you look here, there are the measurements, and these were the actual objects that we measured in an anechoic scenario, in another with different geometry. I mean, everything was different. We produced all samples just in 30 minutes. While compared to AM solver, actually the time will be shockingly higher, actually not usable for this kind of scenarios. Moving towards a totally different things, totally different for RPM, for dimensions, for mass, for shape, for everything. Actually, we had the precision improvement, precision, not accuracy, the precision improvement as expected by digital twins. So in conclusion, and thank you so much for having accepted me till now without killing me. Finally, the point is that data augmentation is useful because blah, blah, blah. But the point is that we must pay attention to the meaningfulness of synthesized data. Okay, that's the main important point. And of course, simplified models can achieve speed and business, and keeping the meaningfulness of the produced features. A single trim parameter is very useful because actually it's something that it's really easily optimizable. And that's not a secondary thing, because you can put a cost function related to one variable. Imagine the advantages of this by an implementative standpoint. And here, okay, this was just to close the slide in some nice way. Opportunities, exactly what we were beginning to do, and we are working on, it's the human gestures, detection of human gestures based on deterministic models. The 25% is something that we found on very, very trivial skeletons with just 4 points, but there is this still limit. If we are able to prove that actually if this work for human is something, if we are able to prove that the sigma is in the same interval also for the human, actually this could be a stable and reference method for achieving the augmentation more than maybe until we will not have more powerful computational platforms. Thank you so much. I hope to don't have annoyed you so much, and we are ready for every question. And thank you again.
Thank you, Marco, for great and completing this topic.
Thank you.